Let's start.
Okay, I put the record mode on. It's on.
Yes, share the screen.
Could you repeat the experiment once?
Sure, we'll do that. Can you see my screen?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes, sir.
Okay, so in today's class, we'll go through the characteristics of different types of incandescent lamps. Different types means we have tungsten filament lamp and carbon filament lamp. Experiment number is 7. First objective is to study the volt ampere, power voltage, resistance voltage characteristics of tungsten and carbon lamps. This is the first one. And then steady state operation of a typical circuit containing both linear and non-linear resistive elements. So first one is obtaining the VI characteristics, and once we obtain the VI characteristics, we'll verify that whatever we are getting, it is demonstrating a non-linear resistive circuit. So your resistance of tungsten and carbon filament lamp, they are not linear in nature. So in the second step, what we'll do in the steady state operation, we'll find the circuit, the current through different lamps, that is your nonlinear resistance, using both linear and nonlinear resistive elements. So we'll be having one external rheostat which will be connected in series with the lamps. So with the help of that, we'll try to show what happens for the steady state operation. That is the second part of it. So this is your carbon filament lamp, which is demonstrating a negative temperature coefficient, and it is not allowed to operate at a high temperature, because at a high temperature carbon lamps start disintegrating. So there will be a blackening of the bulb, which is not recommended. And it is mostly it is used for not for the illumination purpose. It is for heating, and because of some drop we use it. And This is your tungsten filament lamp, and it is filled with the inert gas, and it give its efficacy of the lamps is sufficient for illumination purpose. So we recommend this one for illumination, tungsten filament lamps. So here is a circuit diagram which we will demonstrate today in our laboratory setup. So we are having one auto transformer circuit through which will supply 230 volt 50 hertz AC supply through auto transformer, and we gradually increase the AC voltage from 0 to 220 at the steps of 20 volt. So from here, this will be connected first to rheostat, and through rheostat there are two parallel paths, and in this parallel path we'll connect carbon lamp and tungsten lamp. We'll connect two ammeter for the carbon and tungsten lamp in series, so that we can see the branch current. And then across the lamp we'll add one voltmeter, through which we'll find the voltmeter reading across the lamps. And then what is the input voltage through auto transformer? For that we use another voltmeter V1, through which we'll see the input voltage, and we'll note down the drop across the lamps. And then V1 minus V2 will give you the drop across the external resistance rheostat, which is linear. Okay, and these two are non-linear resistance, because they have one is having positive temperature coefficient and carbon is having negative temperature coefficient. So this is all about the circuit diagram.
And
And
one thing we like to mention over here, since it's a AC circuit, you can see over here the frequency is mentioned here 50 hertz to 30 volt, and all the instruments just beside all the instruments, that is the voltmeter V1, V2, ammeter A1 and E2, you can see over here the MI is written. MI means moving iron instrument for AC current and voltage measurement. Okay, so the voltmeter we have used for V1, it can measure any voltage in between 0 to 300, V2 also 0 to 300, and ammeter, both the ammeters are capable of measuring the current in between 0 to 0.5 ampere. And the rating of the lamps are 40 watt here.
But
Okay.
we'll see that in
Huh.
experiment it can increase. So we have used for one for the tungsten 0, 1, 2. So three range are there, two range are there, 0 to 1, 0 to 2 as per desire. We'll use it. And for the carbon, we prefer milliammeter because it is demonstrating a very low current, right? It is showing low current.
Sir, the measurements are in RMS value, no?
Showing afterwards during the experiment.
The measurements are in RMS value, no?
Definitely. In meter reading, whatever you are getting, that is RMS
That is
value.
RMS value.
Mm,
RMS value.
mm. Okay, so we have a procedure I am not going through because it is already it will be demonstrated through the recording, and then these are the list of the apparatus and rating. And then
Aritruta, 1 minute.
uh, uh,
Ma'am, I have made you as a presenter. Ma'am, you also can present. Yes.
Oh, I have waited for the your approval. Yes, yes, it is given. Thank
Yes.
you. Thank
Okay.
you.
Thank you, ma'am. Yes.
okay. Again, this table will get later. So initially I have given this with I mean this is actually simulated thing. So we will not use now. Just for the demonstration of the uh, graphs, I have used this. So this you have to do once we get the experimental data sheet. So here we are showing that for the carbon, this is the ideal situation when we have a negative temperature coefficient. Its value is like this. And for the tungsten, it is somewhere between tantalum, like in this range. It is not shown actually, but it will demonstrate a positive temperature coefficient. That value is 0.005 per degree centigrade, and it's positive. So it will have a positive slope. It will be between tantalum and this. So this is your VP characteristics and VR characteristics. I have not drawn it for you. Later will come to this. So then the next step is we have to increase the resistance. Initially, when we'll when we'll find the VI characteristics using experiment, we'll just cut out our external resistance, which is your rheostat. So we'll set the rheostat at the 0 position so that no external resistance is connected to the circuit. So for that we'll draw the VI characteristics by gradually increase the voltage from 0 to 220 at the steps of 20.
Aritra sir, please go for the recording. Huh? Then in the recording itself, everything is actually
Oh,
will be
okay,
shown. Huh?
okay,
Will be
okay.
demonstrated, no?
Okay, okay, we'll do that.
Huh. They are also interested to see the experiment.
So let us.
Okay, so in today's class, let us perform the experiment number 7, which is characteristics of carbon and tungsten lamp. So for that, let us first concentrate on the circuit diagram as it is given in your lab manual. You see there are different components. Let us identify them first and then verify that from the circuit, which will be demonstrated right now. So you can see this is the auto transformer or the variac, which will able to provide 0 to 230 volt AC voltage. Okay, so this is the variac part, the corresponding experimental setup. So with this variac, you can increase the voltage from 0 volt to 230 volt. So here we can go at the most 270 as it is seen from the variac dial, but we'll go for this particular experiment till 220. Okay, so this is your main. From here, this is your 230 volt 50 hertz source, which will be going to variac, and from that variac it will go to your circuit. This is the point where the variac is connected. Okay. So next is the rheostat. So you can see from
Aryan
the
Raj, please mute
circuit
yourself.
diagram, from
Aryan
variac
Raj,
it is
mute
going
yourself.
towards rheostat, which is a variable resistance. So this is your rheostat, which is shown in the panel. So it is internally connected, so it is having two terminal. You can see from here. Earlier also in the beginning initial classes it was shown there are two terminal, one is here, another is there, and this is connected at the back side of this board, which you can see from the front side like this. So this is the minimum position and that is the maximum position, so you can vary between these two point, right? This, as you can see, this is your tungsten lamp and this is your carbon lamp, right? And we are using total 2 voltmeter. 1 voltmeter is connected as it is shown across the variac. So this is this one, this is your V1, which I have connected across the variac like this. So these are connected in parallel. I have connected this voltmeter parallel to auto transformer or variac, because auto transformer is connected at this point, right? Then the other voltmeter, which is voltmeter 2, this is connected between rheostat and the variac. Uh, between rheostat, this is your V2, one point of the rheostat, other point is the variac. So in between two I have connected this voltmeter 2. This is your voltmeter 2, which is connected like this. One terminal of the rheostat, other terminal is the terminal of the uh, variac. So this
Basically
is
V2
the two
here
terminal of
it is
the
put across the
variac, right?
lamps to find the.
Then other two are the ammeters. This is the ammeter A1, ammeter reading A1, which is connected for the tungsten, right? So I have connected in series with tungsten. You can see that through rheostat, I have connected the ammeter, and then ammeter is going to the tungsten lamp, and from tungsten lamp it is returning to the terminal of the variac to close the circuit, right? In the same way I have connected another ammeter, which is actually taken in the milliammeter range, because through carbon lamp very low current will be flowing, so it will be easier for us to read if we use milliammeter range ammeter. So we are using that. This is our A2, and that is connected in series with your carbon lamp, right? So you can see that from rheostat again we are connecting this ammeter 2. This is our ammeter 2, and then ammeter 2 through carbon lamp, and carbon lamp to as it is returning to the terminal of the variac. Okay, so this is how we are preparing the circuit. Okay, once more I am demonstrating. Starting from the variac, this variac output is there. Then from variac to rheostat, then from rheostat one terminal is going to this voltmeter, which is measuring the drop across the rheostat, and through this we are closing the circuit. Like this. From rheostat, one path will go to the ammeter A1, and through ammeter A1 to tungsten lamp, and then tungsten lamp to variac. Similarly, other terminal from the rheostat, from there is one another ammeter, which is ammeter 2 for carbon lamp. So from this ammeter we have connected in series with carbon lamp, and from carbon lamp it is closing its circuit at the terminal of the variac. So this is how we complete our circuit. This is all about the circuit connection or preparation of the setup for the experiment. Okay.
So let us now go to the second part to get the data set for the VI characteristics.
Okay, now as our circuit is complete, now we can start taking the reading. So you can see the same reading table 1 I have prepared in rough for the calculation. So we'll go with first with increasing current from 20, 40, 60, 80 in that way till 220, and then once we reach 220 again we'll come back from there in the decreasing case. So at the steps of 20 volts. So this is what we'll do with the rheostat at the minimum position. So this is the minimum position of the rheostat, and with this we are taking the reading. So now it is in the 0 position, so gradually we are increasing the voltage from here, which will be reflected in this voltmeter V1. So this is your voltmeter V1, and if you verify the voltmeter V1 and V2, you will see almost same reading. Okay, and I have connected the voltmeter between in 300 scale, because it is maximum will go to 20, so we cannot go for the 150 volt scale, so we have to read the scale above. Okay, in the dial. So what is the top scale that we have to take? So gradually I am increasing the voltage from 0 to 20, and as it is a nonlinear scale, this is a AC voltmeter, so you cannot see very well, but still this is for 20 here, and then you can check here, this is also for that also we have to take the above scale, and here also it is not very well understood. For the carbon lamp, minimum current is flowing through it, and I have connected for the carbon lamp A2 in the milliammeter, so it is 0 to 100 between, almost close to 0, so very few uh, uh, the magnitude of the current is very low here. And for the tungsten lamp, we can see it is point little more than 0.2, little less than 0.25, so we can record it at 0.25 here for the tungsten lamp, but this will be more clear when we'll tungsten is 0.25, carbon is, let us take point, it is very close to 0, so let us take it as 10 milliampere. This is in milliampere range. Okay, so let us now gradually increase the voltage, so let us go to 40, and again here it is not very well understood what is the difference. From the 60 onwards it will be clearly visible if we keep on increasing. So for 40 also, let us take the reading like this. Here it is 40, there also in that V2 voltmeter it is at the same position. So you can see it is near, it is not actually gone to 40 but close to that actually, and we can see the uh, A1 reading, which is at 0.3 ampere. So 0.3 for tungsten, and for the carbon again here it is little, uh, what we can see between 100 there are 4, so it is approximately 25 we can take. Okay, 25 milliampere for the carbon, and then let us now go to 60. So now here you can see it is clearly visible in the voltmeter V1. If you uh, just see from the top, almost it is close to 60. It is 60. So for the 60 volt V1, what is your V2? V2 is little less than 60 actually, because of the small internal drop. So we can approximately write it as 60, and then we'll take the reading for the tungsten, which is 0.37, and for the carbon it is clearly 50.
Okay, so this is how we should continue and populate the table. I'll just start the next one.
So you can see gradually we have populated till 180. Now let us do again for the 200 and 220. So last few increasing steps. So we are reaching 200. So for that the drop across resistor it should be little less than one. It is what should I say? It is 190, 94 kind of 94, 95 approximately 195 approximately. And this is, if you now go through the milliammeter reading, it is 165, which is for carbon 165 milliampere, and for the tungsten it has reached to almost 0.7. Then this is the final one which will reach to 220. So for 220 drop approximately 214. For the carbon lamp it is 175 milliampere, and for the tungsten it is 0.74. So once we are through now the increasing order, let us now reduce it. So from 220 we'll now reach to 200, noting at the voltmeter V1. So we have reached 200, and then for that what is the voltage drop across resistor, we'll just verify. It has reached around 194 kind of thing, so we are not noting it. We only now have to note down the reading of the ammeter. So for the tungsten it is little less than 0.7, so let us take 0.69, and for the carbon it is little less than 65, so around 163 we can take it. So it is 163, little less. In that way we keep on reducing. So we'll now go to 180. So for 180 let us take the carbon lamp reading. It is 152 or 153 kind of, so we'll take 153. And for the tungsten it is between 6.65 and 66, so let us take 0.65. So in that way we will now complete this table. We are not demonstrating each and every reading, just like that we have to continue.
Sir, one
Now
doubt
let
is
us
there.
perform the steady state operation.
Let it complete,
And
then
with
we'll
that
take it
reading
out.
we'll verify what we are, what actually we are getting from the VI characteristics which we got from this table. Once we plot it, then only we'll be able to get it, and then we will record the steady state value with the maximum voltage, which is 230, as you can see here. This is denoted at V0 in the table 2 for the experiment. So we set it at 230 volt, and then we keep the rheostat in the mid position to have the 50% of the full value, so which will be approximately 100 ohm, because it is a 200 ohm resistor, variable resistor, so max it can reach from 0 to 200 ohm resistance. So when we keep at the 50% position, we get approximately 100 ohm here. Okay, so we'll verify that by recording the drop across the lamps. If you note the reading V2, so this reading is basically what, 230 minus drop across the external resistance than what is applicable over the two lamps which are connected in parallel. So this we can see it is supposed to be 155. Okay, so we have taken this reading which is 155, which is as per the table it will be V10. So this is the drop across your lamps. Then what is the drop across the rheostat? This is your rheostat. So this drop is 230 minus 155. So 230 minus 155, we'll write it here. This is your 230 volt input. 155 is the steady state voltage drop across the lamps, and this I10 and I20 is the steady state current through these two ammeter. So this is the ammeter for the tungsten lamp. So you can see it is 0.61. So we'll record this table parallelly will complete, which is 230. This is 155, and then we record I1 as 0.61, and this I2, which is for the carbon, it is 140 milliampere. So that indicates it is 0.14 ampere. So if we put it there, it is 0.61 plus 0.14. So if you complete this calculation, you will approximately get it as 100 ohm. So we have taken REXT, this is your REXT as 100 ohm, and we got this steady state value. Now let us do it again with the maximum external resistance. Here we'll set it to 200. This is the maximum resistance, which is 200, and for that we just record the voltmeter reading. So voltmeter reading, if you would see here, this is 230 as usual, because we keep it its maximum value, and then drop across the lamps, it will be how much? It is 105 or 110, between that. So let us take 107 something, and then we record the reading across the this is for carbon filament lamp. So this has come as 110, so 0.11 ampere, and for the tungsten this is little less than point, so let us take 0.49. So this is all in ampere. Ampere, this is volt. So once you get this reading, then you can draw the load characteristics at I'll prepare the table characteristics, and then over that I'll overplot this load characteristics, then it will be clear. Then only we can complete the other part, which is the estimated value from the graph. So these two will get from the graph, and then we'll be able to cross check whether the BI characteristics, how much valid we got it, okay, from the plot, right? So with this, our experimental reading, everything is completed. Now we are we have to complete the drawing part, I mean the demonstration part of this table, so that we can get a VI characteristics for the tungsten and carbon lamp. So with this, we conclude the experimental part.
Okay, so once we have all this table complete, or complete the table, then we can, this is our table actually, what this is the experimental value which we recorded, V1, V2, and then with increasing order, the A1 is your tungsten filament lamp ammeter reading. So what is the current through that, and then mean of A1, then for that what is your resistance value. Similarly for carbon filament lamp, what is the current through that with increasing and decreasing voltage, that also we have from the experiment, and then we take the mean of this, and then V1 by A2 will give you the resistance of the carbon lamp, and then total, for the total current we can take the uh, addition of these two, A1 and A2, so that will give you the total current. Okay, so this PPT is already shared with you so that you can get all the values, and then using this V and mean A, we can draw the VI characteristics. So here in the plot we can see this one is your carbon filament lamp, VI characteristics for carbon filament lamp, and this is for the tungsten filament lamp, the green one, and the total current also we plot here, which is in blue. So this we got from the table 1. This is for A2, this is for A1, and this is your total current A. So on top of this, when we plot the load characteristics, then that will give you the current through the circuit. I mean, what is the net current drawn from the source or from the supply. So when we have two setting, right? For the table 2, we have taken from 100 ohm and also for 200 ohm. Like full REXT. So for this 2 REXT value, when we have or when it is an open circuit condition, then it is 230 volt only. When the circuit is open, no current is flowing through it, so it is 230 only. So this point is fixed. And when it is in short circuit mode, that means when instead of putting your the parallel path, if we just remove by a short circuit, then we'll get this current uh, for the 200 ohm resistor, which is 230 divided by 200 ohm, which will give you 1.15, and here it is 2.3 when we have 100 ohm resistor. Load characteristics. So that means whenever you know the total current through it, when REXT is not present, then on top of that, when you take REXT as a load and you draw this load characteristics, the intersection of these two lines will give you the total current, right? Total current through the circuit when REXT is connected with the value of 100 ohm resistance. So that is the total current drawn from the source and from the supply. And for this total current, what is your voltage? That also we need to record, which is turn out to be 155. And at this 155 volt drop across the parallel path, what is your current that we can record? So here we can see that for the tungsten filament lamp at 155 volt voltage, we have a current which is 0.61 ampere, and that for the carbon filament lamp it is 0.15, right? Similarly, when we use REXT, which is 200 ohm, then we have the load characteristics, and that will intersect your total current when REXT is not present. So that intersect at a value of 110 or so. So at 110 volt from the carbon VI characteristics, we get a current which is 0.11, and that for the tungsten we get 0.5 ampere. Okay, this is the estimated steady state current through the steady state branch current through the carbon filament lamp as well as the tungsten filament lamp for two different external resistance. So then next we just write it. So here you can see this is serial number 1, voltage is 230, and here this is 156 from the estimated, and observed value is 155. This is from the experiment. So from the estimated value from the VI characteristics we get I10 means it is through a tungsten filament lamp, which is 0.61, and from the observed value also we got from the experiment it is 0.61, so it is verified. And for the carbon it is a little error, we can see it is 0.0 0.14 and 0.15. So 0.01 ampere is the error in the carbon filament lamp. And in the similar way, when we do it for the other setting, so for that, when we use the 200 ohm external resistance, then we have V10 to V110. Here it is recorded at 107, and for that experimentally a recorded value for the tungsten is 0.49. Here from the graph we get 0.5. For the carbon experimental value at 0.11, from graph also we get 0.11. So we can say it's almost equal. So estimated value from the VI characteristics is almost equal with the observed value. So this validates the proper drawing of the VI characteristics for the carbon and tungsten filament lamp. Okay, so whatever VI characteristics we got, these are nonlinear in nature, and for that we solved graphically, and with that with the value, the calculated value or estimated value is same, almost same as that of experimental value during steady state operation. Okay.
Sir, sir couldn't understand from the graph how are you deriving the estimated value VI characteristics?
Okay, I'm repeating again.
That is negative.
Sorry, what else you told? I could not follow.
Straight lines which represent resistance. Why their slope is negative?
So it is actually load. We are trying to draw the load characteristics, right? So whenever we draw the load characteristics, we should draw like this. So this is your, I'll just take the pen. So V minus V, or rather we'll write V1 minus IR1 is equal to V2, which is your drop across the this thing, drop across your lamps. So whenever you have R is equal, for particular R, say R equal to 100. Okay. So then when I equal to, when it is an open circuit, when it is open circuit, then what you write? When there is open circuit means no current is flowing through it. So V1 is your 230 volt, isn't it? V1 is through auto transformer. So you set maximum voltage, which is 230. When I is not flowing through it, you are getting what? You are getting V2 is equal to 230. 230 current 0. Right? Whenever you short the terminal, like when you, instead of, when you have two lamps, like this is your circuit, when you short this to terminal, then voltage drop across it will be 0. So what is your current then? Current is equal to V1 divided by 100. V1 is your 230 volts thing. So for that you got 2.3 ampere. Okay. So you have now this current, which is 0, this point, which is 0, 2.3, and you have this point 230. So if you join these two line, then with this you can show all what happened in the intermediate step. Whenever you have some other value of current, then you can effectively represent this, right? So that is why you are getting this, because of this drop in the nature, in you are getting a load characteristics like this. This is called load characteristics.
And
Madam,
not
want to
only,
say? Madam,
yes, yes.
V2
And not
according
only that, it is in the form of y is equal to mx plus c. So what is the x coordinate here? X coordinate is v1, right? And y coordinate is I. Am I correct? Hello?
no, so V x coordinate is V2 and y coordinate
No,
is
x
I.
coordinate is v1 and y coordinate is y.
I current VI characteristics.
I. Y is I. So what is coming over here? Hello? 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 IR is equal
Yes.
to
I'm
V1
writing
minus
also.
V2.
It is X minus some value. Uh,
Hmm. Hmm. Yes.
so what is your Y is equal?
X minus C by M.
So you have negative slope.
No. This will be plus.
प्लस 1 by mx आएगा.
हाँ, y by m, x by m minus c by m.
बोलो इधर. बोलो भाई.
What? Hello?
Then
I think
slope
Hello?
is positive.
Yes.
it is a positive slope, no, ma'am.
Then why the graph is in negative slope?
Do you know how to draw this y is equal to mx plus c? Hello?
Yes, ma'am.
You're
खाइलो आर की करो.
Hello?
Yes, ma'am, you are audible.
Audible, na?
Yes, ma'am.
Yes, ma'am, yes.
Hello?
Yes, ma'am, you are audible.
Acha. So, this, if you see this, huh? So, have you understood this one, b1 minus b2 is equal to IR?
Yes, ma'am.
Yes, ma'am.
Huh? So V1 is the total voltage, V2 is the voltage across the lamps, and this is the drop, IR is the drop across the external resistance which is working as the load over here. Understood?
Yes, ma'am.
So I is equal to therefore V1 by R minus V2 by R. Clear?
Yes, ma'am.
Yes, ma'am. But why the slope is negative? Because we are plotting the graph I and V1, and so slope must be then. Why the
Acha.
slope is negative? The question.
Now look at here. First we want to represent the what is our idea. Idea is that when R is not present, that means we are on the x-axis, then V1 equal to V2. So that what it is 230, right? And 230 means you can change the voltage also.
Ma'am, here we are plotting
the
V1.
problem is we are not drawing v1 as a x. Take v2 as a x and
V2 as
this
x.
then your slope will become minus and y-intercept c will
V2
be 2.3. Then
V2
you will
as the
get the
minus.
plot.
V2
Because
V2.
when we short the
Ma'am,
load
this
terminal,
is
it
the
is
IV characteristics, na?
IV characteristics.
So you have told that V1 and V2 should be there. So in the y-axis there is I. So how can?
Arey,
madam, I'm writing it again. So for the
you write it better.
v1 minus I r is equal to 100. I'm writing for 100. Okay, so I into 100 is equal to your
I
v2.
is equal to V2.
Is equal to v2. Now write v1 is equal to v1, whatever it is value is 230. That is fixed.
No. First you write it in the y is equal to mx plus c form, then go below.
I'm writing that only. So I
That.
instead of I will write y into 100 and then v2 is equal to your x.
V2 is equal to x.
Then what? Then y is equal to y is equal to
Y is
x by
equal to
minus
minus x by 100.
0.01
1
x
x
plus plus
plus
2.3. So now you compare
now you
2.3 is
compare
your
Yes,
this.
yes.
intercept
Now it is clear.
Now it is
and now
okay.
it's
Yes,
okay.
ma'am. Yes, ma'am.
Yes,
So
ma'am.
now when it is 200, then you get the other thing because your y-intercept will change.
Y
It will become now
go
1.15.
for any other voltage.
Yes, sir. Sir, my previous question was from VI characteristics, how are you deriving the plots like arrowheads, which you have black arrowheads? From that you are estimating table 2, sir. What is the
I'm coming to that now. The once we get the vi characteristic, then with this sorry, once we get the load characteristics, then for the intermediate thing, everything we are having, like when there is a intermediate value, for any value we can get the value of the voltage v2, isn't it? That is what we are trying to do. How we have the total, whenever the rext is not present, then we, for that we have your nonlinear load character, total current characteristics, which is the sum of a1 and a2, which is this blue. Okay, so when these two will intersect, that will give you now the total current through the circuit when we have rext in the circuit, isn't it? Blue one is when rext equal to 0. So now when we have rext equal to 100, then what is the total current drawn from the supply? So that we can find out from here. So this is the intersect point.
Sir, could not
And
follow this one, sir.
huh?
That sir, Rext equal to 0, we get that blue line. Then after that could not follow.
Okay, so this we got VI characteristics without REXT in the circuit. Now when the REXT is there in the circuit, then of course this value no longer will be correct, isn't it? Whatever I mean you are getting for the no load characteristics, that means no REXT in the circuit. So now we have to solve it using graphically. When we try to solve it graphically, we have to take the REXT characteristics, which is this. So when they'll intersect these 2 points, this is your no load characteristics and this is with load. So when these two intersect, we'll get the voltage drop across the V2 across the graph, across the lamps, and what is the total current drawn. So at this point of intersect, we get the total current drawn from the supply, and for that, what is your voltage drop, what is the voltage drop across the lamps, that also will get, which is 155. So at 155, this is your 155. So at 155, what is your current through the uh, uh, tungsten filament lamp and carbon filament lamp? For that, we are taking help of these two VI characteristics. Like green one is for the tungsten, so at 155 we have drawn the VI characteristics for uh, tungsten filament lamp. So from 155 volt drop, what is the current that we can find from this graph? So which is 0.61, right? In the same way, we have the VI characteristics for the carbon filament lamp. So at 155 volt, what is the value of uh, mm, uh, current through the carbon filament lamp? That also we record from the graph. And the same way we do it for the when REXT is equal to 200 by the yellow thing. Now is it clear?
Sir, that green line is for the tungsten when Rext is 0, right?
REXT is 0, right?
So I'm sorry, but that part is still confusing for me. Means, will it
If
be possible?
rext is present there, then we have drawn it for without external resistance. So when external resistance is there, then of course the value will change. What initially we were setting for 0, 20, 40 in that way. So whenever the rext will be there, so whatever you are setting through the input 0, 20, 40, that is actually not 0, 20, 40 for the v2, I mean drop across the r2 na, drop across the lamps. So for that we need to take care of the load characteristics. Can you follow now? Because whenever rext is there, your v1 is not equal to v2 na, v2 will be less than v1. So that how could we take care of when we have the r external? So that is for that we are using this load
Yeah,
characteristics.
here the method is shown over here that when the load is present and when the load is absent, and we have to correlate in between this. How? When 230 volt is present and the resistances at external resistance is 230 volt is provided and to external resistance is present, then at a single point this two characteristics with load and without load intersect with each other, and this is the point where it gives us the voltage across the lamp. You see previously, if the previous graph you follow, then it should be 230 if 230 is given. So the lamps will also get 230, but you can see over here it is giving that when 230 is given but the resistance is 100 ohm, what is the voltage appearing across the lamp? That is comes down to 155. And this theoretical approach, this theoretical derivation is also being established through the experimentation, and that's what the table shows, demonstrates you. Understood?
Table 2, yes.
Table 2.
And that also validates the proper drawing of VI characteristics. Whatever you got, that is correct or not. That maybe if it is wrong, if your VI characteristics is wrong, then definitely whatever current you are getting, it should not match with your experimental value. What you have recorded from the experiment.
That is a theoretical approach or graphical approach, you can say. That is a correlation between the load characteristics and no load characteristics, and that is being established through the in addition it is being actually the experiment is to show the negative resistance characteristics of the carbon lamp and the nonlinear characteristics of the tungsten lamp. In addition, here the extra derivation is given that how to correlate between the no load and load characteristics, not only the theoretical but as the veracity of the theoretical derivation has been proved through the experimentation what has been tabulated in table number 2. Understood? So 230, although 230 volt is applied, if it is no load characteristics, then 230 volt itself will appear across the lamps. But here it is shown from the intersection point of the no load characteristics and load characteristics that the voltage across the lamps at R is equal to R external or R load, you can think about as 100 ohm, it is come down to 155, and when it is given as 200, it again come down to very lower value, that is 110 because the resistance increases, so voltage across that one increases again, so that is 110. Okay. And
so
also
similarly, if you go for another REXT, say 500, then another thing will come like this, and you will get even lower value of voltage if you take the intersection. So it will come down to around 40ish, that kind of thing. And if you take REXT to be 0, then actually it should be somewhere here, isn't it? Like the next set of data. So to show this from 0 to say very low to very high REXT, what happens we can get from this plot only. That is why we draw it only for no load, so that whenever additional load we can add in, then we can get the value from graph. That is also another part apart from what madam told. Okay. I hope now it is clear.
For various RXT, you can get it from here only. You no need to go for any experimentation. Once you have drawn the no load characteristics and you know the your R external or R load, you can easily get it from graphically, from this graph only. No need of any experimentation at all, because the experimental veracity of the results have already been shown to you. Understood?
Ma'am, I got that when we increase the resistance, the voltage across the lamps get decreased. But that intersection portion is I'm getting confused. But I think the class has been disturbed, means getting delayed because I'm.
No. We don't have any problem. We are very happy to have such a discussion with you. We encourage such a discussion.
But that intersection means that we are intersecting, and that's how
Intersection the load characteristics with the no load characteristics, which gives us the idea of the voltage appearing across the lamps, that was V2, and what is the total current flowing at this moment. Steady state current, obviously. Steady state current, not only the total current, as well as when you dropping the perpendicular on the V2 axis from this intersection point, it also gives you the individual current flowing through these two parallel branches, which is nothing but the lamps.
Okay, ma'am.
This is, let me here it is the intersection point where it intersects with the total current. Now we are dropping the perpendicular. Now the perpendicular on this x-axis gives you the v2. Now here it also intersects, this perpendicular intersects with the individual currents through the parallel branches, and that parallel branches current are two this two. Understood? Is it this red line, this red line?
This
Understood?
one.
This one, this two, this two. Clear?
Okay, ma'am.
Okay.
You are from section I or J?
I section I.
Okay, I'll discuss in class again with some problem. If we have the nonlinear resistance, how can we solve graphically? There are some problem which I'll try to discuss in the next class. Okay.
Okay, sir. Thank you also.
So now
Go to the
once
next
we
slide. You can see over here.
uh,
Here it is tabulated. Okay. Last slide.
so discussion how we'll interpret VI characteristics of two different incandescent lamp. This is actually just you have to, I am not giving you the complete answer. You write in your report because all the thing is almost done for you. So you try to answer from the point of view of slope or conductance of resistance of the VI characteristics. Okay. Carbon is having negative temperature coefficient, tungsten is having positive temperature coefficient. So from the VI characteristics, how can you interpret which one is carbon and which one is tungsten? So that you have to answer. Okay. So I repeat, you have to answer from the point of view of conductance or resistance, from the slope of the graph. Okay, got it. So whether slope is increasing, whether slope is decreasing, what happens? Looking at that, you should identify which is carbon and which is tungsten. Why do the reading differ for the increasing and decreasing value of the lamp voltage? So keeping in mind that whenever it is increasing, then of course your I square R will be more, and then there'll be heating effect. So then on top of that, what happens if there is a heating effect? Then what changes you will find in the carbon and tungsten filament lamp? And from the point of view, you can tell that the values are changing for the increasing and decreasing. So you will find that there may be hysteresis kind of thing. So this is the clue for the answer. Account for differences, if any, between the predicted and observed steady state operating points of the circuit. So what you think that you write, if the VI characteristics is not drawn properly, then there will be chances that what you are getting experimentally is not actually from the graphic estimated thing is not same as the experimental. So then in that case it will give you the different value. So we have to, that is why how can we improve it? We can even go for the lower step. If we get such kind of thing, then we can go for the low steps. Instead of 20, we can go at the steps of 10, and we populate more number of data, and then probably we'll get a better result. Okay, in that case. So conclusion is characteristics of carbon tungsten filament lamp has been demonstrated, exemplified. Nonlinearity of the filament resistance is also demonstrated. Temperature coefficient can be interpreted, we can interpret from the VI characteristics, and what is positive, what is negative, that also we can say. Okay, so these are the conclusion which you should write in your report. Okay, so I don't have any other thing to discuss. Madam, please take over.
Yes. No need of any discussion further required for this. Already we have discussed a lot. Now their turn to write down the reports, as well as they have already got the slides, so they can write down the reports in the report format, and the manual also I think they have with them. So complete the report. Okay. with title objective, then observation table, and results discussion and graphs obviously. And what are the graphs required to be given? VI characteristics.
Others are also
Uh,
mentioned.
which
Uh,
manual are you saying about?
your
Man,
EES51 for the electrical technology lab, one manual has been provided, na?
lab manual provided to you. If it is not, then we will post it.
Is it the
No, it is
slide?
there. It is there already in team.
Hmm.
Okay, sir.
Okay, so this
Okay,
is
so
all.
you have to draw these three characteristics: volt ampere, power voltage, resistance voltage characteristics of carbon and tungsten lamps. So it is given in the manual only.
And ma'am, one thing, when do we have to submit or something like that for the report and all?
Within 1 week. That means when we start your lab class next week, before that you need to submit. Before that means that is the latest. By latest, latest by Monday morning. Try to submit before it.
But we have to submit
Where do
this
we?
all the practicals, previous practicals.
You have
I think
submitted report submitted for previous practicals?
No, no,
No.
ma'am. Sir has not told to submit
No, ma'am.
anything.
Okay,
That is
okay. Then for that we will discuss among ourselves and we will let you know.
Okay, ma'am.
So on
And ma'am,
partial
Where do we
we
make
have
in
to.
practical copy or in A4 size
on
paper?
We will let you know everything.
Okay, ma'am.
Okay. So you can leave now. Aritra sir, they can leave now?
yes.
Okay.
ম্যাম তাহলে আমাদের এখন তো কিছু করতে হবে না, যে ওটা জানানোর পর সাবমিট
হ্যাঁ
করে।
হ্যাঁ 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 একদম একদম।
ওকে ম্যাম, থ্যাংক ইউ।
থ্যাংক ইউ থ্যাংক ইউ।
Okay, ma'am. I am leaving then, huh?